This video is going to walk through an example using the SIR model. Alright, so the disease that we are going to focus on for this example is called the respiratory syncytial virus. Okay, you can see the description from the CDC website there. I'll let you pause the video and read it at your own, or on your own if you prefer. Okay, so the example that we are going to work through assumes that the respiratory syncytial virus is working through the population of New York City. Okay, so the population of New York City is 8.41 million. They experience an outbreak of a strain of RSV, so the respiratory syncytial virus. Everybody eventually recovers after 9 days and grants lifelong immunity once recovered. Okay, so once the epidemic was declared, 30,000 people were infected, 600,000 were already immune to the disease, and then it says some other information here. So suppose that a susceptible person, so a person who has not fallen ill with the disease yet, has a 0.0003% chance of contacting a member of the infected population, and if contact occurs, 1 out of every 20 people will fall ill. Okay, so you have essentially a 1 out of 20 chance of falling ill with the disease if you contact the person with the disease. Okay, so just kind of organizing the data here. The infected population, it says that there are 30,000 people in the infected population. Okay, and then the recovered, it said, okay, we're already immune to the disease. That's actually the same as being in the recovered population because, again, if you're in the recovered population, you're granted lifelong immunity. So this is 600,000. Alright, and then this is a susceptible population. Well, we know that there are 8.41 million people total, so I would have to do 8410 and then 000 minus 30,000 minus 600,000, and that ends up being 778,000. Okay, so 7,780,000 people are in the susceptible population. Alright, so now we have our data organized here, at least the numbers that correspond to the population. And again, working through the SIR model, I need to know the recovery and transmission coefficients. Okay, so again, recovery coefficient is B, transmission coefficient is A, and then from that I can get my rate of change equation. So B is the rate at which the coefficient that allows us to compute the rate of change in the recovered population. And so this is really 1 out of however long it takes to recover from the disease. So this is 1 out of 9. I'm going to use the approximation 0.111 for this. Okay. And then P, again, P is the chance of contacting a member with the disease. And so that is, according to the prompt, this 0.003%. I'm going to represent that as a decimal, so that's 5 zeros. 1, 2, 3, 4, 5 with a 3 after it. And then Q is the chance of, okay, if you contact them, what's the chance that you fall ill with the disease? So this is 1 out of 20, which if we use a decimal, 0.05. Okay, so 5% chance. Okay, and then so this means that A, if you do the math, you multiply those two, this is 0.1234565. So there's 0.6 zeros and then 15. Alright, so then this gives us this allows us to fill in our S prime, I prime, R prime, and so this is minus ASI. Okay, and if I write that out, that's minus, and then the 0.123456515 times S times I. I prime was minus ASI, or sorry, plus ASI minus BI. Okay, and R prime was BI. Okay, so now just going to fill this in. So 0.1234565 times S times I minus B was 1 out of 9, but I'm going to use the decimal approximation. 0.111 times I. And then the last one here is 0.111 times I. Okay, so I have those rate of change equations. And so continuing on, I'm just repeated everything I have here. I want to be able to know how the population changes over time. So my question is, I want to know what are the populations of the various compartments on day 1. Okay, well, I can use the information that I have already collected to determine this. I can determine the rate of change, and then from using a sort of iterative process, if I just think of the new population value as whatever I started with plus the change, then I can compute the next one. So for this change value though, I'm going to use the approximation where I take S prime, so that's these values that I compute from the rate of change equations, times the time step. So this is the change in time. Okay, so we'll get there, but essentially, since I'm progressing 1 day into the future, it'll be +1. If I was doing 2 days at a time, it would be 2. If I was going backwards in time, it would be -1. Okay, but if I compute S prime, I prime, R prime, okay, so I would enter negative 0.00000015 times S, which is 7780123, times I, which is 30,000. This is going to give me negative 35010. Okay, and then similarly, I prime, I'll let you do that computation. You end up getting 3676.67. Okay, so again, it would just be putting in these values, so S and I, into the equation for I prime, and then R prime, I can write that out pretty quick. So 0.111 times the not 600,000 times 30,000. 30,000. Okay, because that was the value of I. Okay, and this ends up being 3,333.33. Repeating. Okay, so then to get the values when t is equal to 1 for S, I, and R, I would take, again, I would use the equation that I have starred here in blue, and I would take the old population, so 7, 7, 8, 1, 2, 3, 4, plus, and then delta S, where delta S is S prime times delta T. So S prime we found to be negative 35010, and then I would multiply that by the change in time, right? So change in time, I'm progressing 1 day into the future. Okay, and then this would give me 7,700,444, or 744,990. Okay, similarly, I prime, you do 30,000 plus whatever the change was, so it's increasing by 31,676,000 or 676.67 times the time step, which is 1, and then you get 61,676.76. And similarly for R prime, you end up getting 603,333.33. Okay, so now this would be a long process to do by hand. So what we want to do is we want to use Excel to help us out. Okay, so I made a template which is available on a Moodle course page associated to the course for this video. Okay, so feel free to open that or download that and open it. But essentially you could make a spreadsheet where you have time, so T is time, so this would be time in days. S, I, and R would be the population values in each of the compartments, and then the rates of change. I also added 2 check columns. I'll tell you when we get there what you should get in those, and then I also made a spot for the transmission coefficient and recovery coefficient. Okay, so we began with 778 or 7,780,000 in the susceptible population, 30,000 in the infected. Recovered was 600,000. Okay, now the check column I added, so this should be, if you add up the S, I, and R, it should be the total population of New York City in this case. Okay, so every time that you do this calculation, you should get the population value, since nobody is entering or leaving the city and nobody's dying. Okay. Alright, so next I want to compute formula or compute the S prime, I prime, and R prime values that we got by hand. To do that, I would recommend computing the transmission and recovery coefficient first. So A, the transmission coefficient, we said that was the chance of coming in contact with an infected person, so that was 0.0000003, and then times by 1 out of 20 for the chance of contact. Okay, and then the recovery coefficient, we said that was equal to 1 divided by 9 because it took 9 days to recover from the disease. Okay, so I have those in here, and the reason I put those in their own cells is because I'm going to use cell referencing. So, and we also have the rate of change equations for this stuff, so I'm going to enter that as well. So equals, to begin a formula, S prime was A, so I'm going to click on the cell that I had my transmission coefficient in, and then I need to freeze that value because eventually I want to fill in this entire table, but I don't want that value changing. So on your computer, if you're doing this, you may be able to hit F4 if you have a function lock on your computer. If not, you may have to hold FN and hit F4 to insert money signs so they look like money signs. That just denotes absolute cell referencing, so you're not changing that value as you drag down. Okay, and I forgot a minus sign. So again, the formula for S prime was minus, and then A times S, so I'm going to click on the cell with the population value in it, times I, so again the cell with the population for infected in it, and then hit enter. Okay, and I got that same value I computed before. I prime is A, okay, and then freeze that, so FN F4 for me, times S times I, okay, and then minus B, okay, so click on B, and then you have to freeze that as well, so money signs around that, times I. Okay, everything's matching so far, and then R is the R prime is just B, okay, and then make sure to freeze that, times I, okay, and then so that is S prime, I prime, R prime. The check here, okay, so nobody's leaving the city, nobody's dying, so everybody needs to be accounted for, so the total change, if we add up all these changes, it should be 0, which it is. Okay, so that's good. Now, to get the next row, again, I need to do that process that we did for day 1, so I need to take the previous value of the susceptible population, so click on the cell corresponding to the susceptible population at day 0 and add to it the change in S times 1, because my time step is 1. Okay, I'm going to repeat that with the other formulas. Oops. And here I made an error. I need to add, not multiply. And then equals recovered plus change in recovered times 1. Okay. Then I want to add those up, so I can click on the little box in the lower right corner to repeat that formula. Still checks out. Okay. And then I need to compute S prime, I prime, R prime. And to do that, I'm going to highlight those 3 cells, click on the little box in the lower right corner, so when my cursor turns to a black cross, drag those down to repeat the calculation. Okay, and then I want to check to make sure that they're equal to 0. Okay, so now at this point, the formulas are complete, and I can highlight that row and drag it down. I have it set up to go through 21. Okay, and so I get the change, or the different population values and how they change over time. Okay, so this whole column, column I and column E, those values should stay constant. If you are getting something where it is not constant, so if I is not 0 or if E is not your population value, then you should redo your formulas and double check your formulas. Okay, so with this, now we can continue the analysis. Alright, so next we may want to determine a threshold of a function, and a threshold is just simply a number needed for the population to change in some way. And so what we're going to look for is the threshold of infection, so where infection starts to decrease. So the threshold is going to actually be the number of susceptible population, so how low the susceptible population needs to get before the infection starts to die off. So really what we're looking for is when the change in the infected compartment is 0. So again, that would be, if we go back to our initial studies of the graphs of S, I, and R, remember I had the graph of the I population, it reached a maximum and then it decreased over time. Okay, so this time value is what I'm looking for. So I want to determine that time value, and then that is going to correspond to how low the susceptible population needs to be. Now, to find this value, that is when I prime is equal to 0, because again, I prime over here is positive. So this is I prime was greater than 0. Here, I prime was less than 0. And right at this point, that's when I prime is equal to 0. And I want to find that value. Going through the mathematics, you can see what I've done here. We can't ever have I is equal to 0, so we would discard that. So we're left with this part of the solution, and that leads to the threshold value for the susceptible population being B over A. Okay, and if I do that with my values, so again, B was 0.111, and then A was 0.1234565, and this ends up being 740,740. Okay, so if I go back to my Excel table, I need to find when the susceptible population, where in here that occurs. So I'm looking for 740,000. That occurs right between days 8 and 9. And so what I should see is if I look in the the rate of change in the infected compartment population, if I look there, that should change from a positive value, which it does, from a positive value to a negative value. Okay, that indicates to me that the threshold is within that day range. Okay, so just as a summary here, So again, the time when S is equal to that, what I should see, so if this is that value, I prime should be increasing before that time value. And then after this time value, it should be decreasing. So again, I prime would be positive here, positive, and then again this would be like day 8 or 9, somewhere between those two. We don't know the exact day, but after this we should see I prime being negative. Okay. And then lastly, sometimes a quarantine may be put into place. So if it was put into effect on day 0 and it says it reduced the chance of contracting the disease by a factor of 30. Okay, was it effective in stopping or slowing the spread of the disease? So what we need to do is say, okay, well, if A was this, okay, so if A was this, the new transmission coefficient, it may change, okay? And in fact it does, because, well, it would decrease the chance of contracting the disease by a factor of 30. So in essence it's taking A and dividing it by 30. And so as a value this ends up being 0. And then it's 8 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 5. Okay, and then the recovery coefficient doesn't change. Okay, so people are still going to recover at a rate of 1. That is, or the recovery coefficient is still going to be 1 out of 9. So it's just equal to B. Okay. Now to see how this changes, we can look through. We have the data for when the recovery or the transmission coefficient was just this, and so if I take this now and multiply by 1 divided by 30, okay, I get that same thing. And when I did that, the values actually changed quite drastically. Okay, so you can see that my table automatically updated. So the rate of change in susceptible and infected is different. Recovery is still the same. Okay, and now what we're seeing is that people are falling ill slower. Okay, so we're seeing, okay, 30,000, that number of infected is still increasing. The susceptible population, so if you looked before at day 21, it was something like in the single digits remaining. Now we're up in the 7 millions. So it was fairly effective at reducing the rate, or reducing the rate at which the disease spread through the population. Okay, and then one thing I want you to think about, I'm not going to do it in this video, but how does the threshold change in this situation? So again, the new threshold is going to be different than the old threshold, and so what does that mean for the population?